geological subsurface formation that is saturated with water, that is bounded above and beneath by some low hydraulic conductivity confining beds. And if you drill a well into a confined aquifer, water level in wells will try to rise to a certain potential. We call this hydraulic head of the aquifer, which reflects the energy level in the aquifer. Of course, when we build a computer model, we write equations for flow in the confined aquifer. Here is a typical equation we can write, lifted out of the model flow documentation. So we have hydraulic head, where the water level rises in the wells. And we have hydraulic conductivity in 3 different directions: x direction, y direction, z direction. In aquifers, conductivity can be direction dependent, so it's generally a tensor. W represents some sort of a source sink term. For example, we may have leakage through the top of the aquifer. That leakage will be an aerial source term. We can also take water out by pumping water out. Then we have a point sink term. So that's a confined aquifer. Another class of aquifers we're looking at are called unconfined aquifers. Usually these are defined as a body of water that is bounded above by the water table and beneath by some low conductivity confining unit. The water table is a location where you have dry zone above versus a fully saturated zone beneath. So we call it the water table. Unconfined aquifer has a different set of equations. Here we write a set of equations in an XY coordinate. So we look at the aquifer in a map view. And we see unconfined aquifer equation for the hydraulic head. Now the hydraulic head describes the height of the saturated thickness. It's nonlinear. So we have derivative of head times the head. And the unconfined aquifer is also special. It is bounded by this water table, which is our unknown hydraulic head, which is simultaneously also the unknown boundary condition. So unconfined aquifer is a really tough problem to solve.
So what is, wait a minute, the model? You are in the math department, you are interested in the model. What is S?
Oh, S is the coefficient of storage. For unconfined aquifer, we call the specific yield. This relates to the efficiency of draining water from dry to wet zone. In our this talk, we do not deal with transient problems. So our equation, this is something storage coefficient. Since we don't care about transient aquifer responses, we basically have 0 in the right-hand side.
Okay, but then the first model you take X, Y, Z, and then you are dealing just with X and Y.
For the unconfined aquifers.
For what?
For the unconfined aquifers, generally we write 2-dimensional equations.
Okay.
We often ignore vertical flow because the equation is more nonlinear and more difficult to analyze. So for confined aquifer,
you are making an approximation.
If the vertical flow component is very small, we can approximate the 3-dimensional flow field by a 2-dimensional flow field.
Okay, so
then
you are taking it in domain. It's like you are taking it in domain.
Yeah, kind of like that.
Okay.
So yeah, so feel free to ask questions.
Of course.
And inversion, a little bit of history. Before 1970s, aquifer inversion was typically done using type curves developed from analytical solutions of aquifer problems, which are generally, we assume that aquifers were homogeneous, isotropic, of simple geometry, and of infinite extent. So with those assumptions, the previous equation can be solved to give us analytical solutions. And then we fit field measurement data to these type curves, from which we can infer aquifer parameters. I don't know why this happens. Okay. Please. I don't know why this one's so high. And with the advent of modern computers, computer modeling becomes the norm. So instead of assuming aquifers to be very simple, which it really doesn't exist in the real world, we can use computer codes to explicitly solving the forward flow equations, the 2 equations I've just shown, for very complex geometry, multi-dimensional heterogeneous aquifers. And simplifying assumptions required by analytical solutions are not needed for forward modeling. And we have a direct impact on aquifer inversion. So instead of relying on analytical inversion, computer-aided numerical inverse methods have been developed since the 70s. Typically, we create some sort of objective functions which describe the mismatch between model-simulated data and observed data. The model may predict heads at a location. You compare that with what you measure in the field. Then the forward model is solved repeatedly with different sets of parameters until one set of parameters are found that lead to the best, which means the smallest model or field data misfit. So this is as a result of computer, we now do computer-aided inversion. Analytical inversion gradually fell out of fashion, though still some consultants still choose to use them. Because sometimes we just look at water supply problems. The consultants don't want to think about heterogeneity. So they will assume that the aquifer is still homogeneous and they still use analytical solution for inversion. But generally, numerical inversion nowadays dominates. Our talk is that, I hope you can still see, it's kind of low. Analytical solutions actually describe physics of flow in its solution. So can we try to bring analytical solution back to numerical inversion? That's a key point of this talk. So that's our takeaway message. We figured out a way to bring analytical solution back to numerical inversion. Okay, here's an example of analytical inversion, which I teach in my hydrology class in geology. You have a confined aquifer, you have a potential metric surface. If you pump the aquifer at a certain rate, you can observe the gradual decline of the potential over time. For example, water level in an observation well. From this decline over time, you can then solve the confined flow equation. Of course, we are assuming aquifer is homogeneous isotropic of constant. T is integration of hydraulic conductivity over the saturated thickness of the aquifer. So it's, in a measure, it's the same thing as conductivity. S is the integrated storage coefficient in the vertical direction. If we assume homogeneous aquifer, we can solve the flow equations. Then we can develop a type curve, the classic Theis 1946 solution. And we actually, in my class, I will derive how we find the Theis solution. Then we can fit the observed head change with time against the analytical solution, from which we infer the aquifer T and S.
So in this case, this model, just a question about the model, you are writing everything in
radial coordinate from wells.
You are changing coordinates now.
We actually write the Cartesian coordinate, then we do a coordinate transform.
Yeah.
Then we solve in a radial coordinate, because this is a homogeneous isotropic system. So we don't need to do in a Cartesian.
Now you have, so this is, if I look at it as a math problem, this is like a second order nonlinear problem, right?
Yes.
Problem. And then you have boundary conditions.
Oh, okay.
Can you say something about the boundary conditions?
There's a transient problem. So we have initial condition head. When T is 0 initially, before pumping, we have some observed potential. It means this initial condition. Boundary conditions are two. One boundary condition means when at all times, when the distance from pumping well is far away, the head is not influenced by pumping. So the head is always sits at the initial values. Another boundary condition is written right at the well, which is a form of continuity to impose flow continuity at the wells. I mean, this is not a talk about analytical solution. I was sort of showing you that example.
Of course, but you are in math department, you would like to understand the model.
Oh, okay, yeah.
I mean, for us.
Could I ask a question?
Yes.
Can you say a few things more, a little bit more about inversion? What, by inversion, you mean you have the H and you're looking for the parameters in
Yes.
the differential equation?
Yes.
And in this equation, if you know H, you're done, right?
Yes, you will know H from measurements.
Yes.
You will measure the H, then you compare the measurement against this mathematical function.
So what is the difference? What are the parameters in this problem?
Transmissibility and storativity.
S and T.
Yes.
And that's just the algebraic equation that you solve once you know H.
Yes, we basically describe a curve, which is a mathematical function. Then we move around the curve to fit the observed head changes with time. Then from the fitting, we can find out the location when the two curves are fit together. Then we can infer the solutions. Does that make sense? This takes like 3 classes almost.
This looks to me is SMT. Are SMT dependent on H?
T is a hydraulic conductivity integrated over in the vertical direction. S is a specific storage coefficient integrated over the saturated thickness. So this is again, we solve 3D problem to 1D, then we infer parameters that are integrated in the vertical direction.
If I know the functional form of H in terms of position and time, that top equation, your PDE, is the algebraic equation for S over T.
Oh, okay.
I'm just visualizing this, but
right.
Because I'm missing the point that you're making.
Okay, here I'm just have a quick slide about analytical traditional inversion, assuming homogeneous aquifer properties. Then we simplify the mathematical equations. Then from simplified equation, we derive explicit solutions, which we then fit with field data. And this is something we teach in intro hydrology, but mostly if you work in the real world, we don't do this type of problems. We do numerical inversion. I'm not sure if I answer your question.
But that's
Okay.
okay.
Usually they don't have age. They only have some measurement of age.
Yeah, I don't know what's done.
But you wouldn't, if you fit a curve to that or fit something.
Then there is a lot of uncertainty, right?
Because you're assuming a homogeneous formation.
Yeah, in this case, you're right.
Right.
But in what she will be talking, I mean.
Yes, heterogeneous case. And actually,
you only know at few locations, age, and then from there you have to infer the parameters.
yes, we will show you more sort of the modern example where the aquifer is not as simple as that. Then we have to use numerical methods. I hope this one, I think is freezing. Okay. This is another, okay, we'll go through very quickly. This is unconfined case. You have some reservoirs. This is aquifer. If you rain on it, water level rises up. There's a well-known analytical solution, which is a function of conductivity of the aquifer as well as the recharge rate. So, simplifying situation, we can write analytical solutions. And if you fit some observed heads with this function, you can back out the parameters. Traditional methods. Traditional method, as we say, we have to assume basically homogeneous system, sometimes infinite extent. So that really does not work with most of the real world situations. That's why we rely on numerical inversion. But the reason my group developed a new numerical inverse method is that existing numerical methods have some serious issues. One issue is that existing numerical inverse methods assume that the boundary condition of the aquifer, which will become boundary condition of your mathematical equations, must be known or can be determined from model calibration. In the subsurface, boundary condition is rarely known because we have limited access. And when the problem of interest is far away from known hydrological features, so if we have aquifer far away from the 2 lakes with known heads, we don't know the boundary condition near the aquifer. Secondly, boundary condition calibration can lead to non-uniqueness of the calibrated parameters, boundary condition, and flow field. I will show you what I mean next. Non-uniqueness means multiple sets of parameters and boundary conditions can together satisfy the model calibration criteria of minimizing the mismatch between model simulated values, objective function, between model simulation versus the observed field data. As a consequence, many models, numerically calibrated models, are non-unique, which means another set of parameter boundary conditions can equally calibrate to the observed field data. And this is an example why I say boundary condition can cause non-uniqueness. For example, we have a 2-dimensional XY homogeneous isotropic aquifer for which we can develop analytical solution. And here are 2 examples of solutions. One solution on the left-hand side is driven by a set of fairly linear boundary conditions. So this will be hydraulic head along the model boundary. If we drive the left-hand side flow field with this boundary, we find out this flow field satisfies the observation data of 3 observed heads and 1 flow rate. Okay, we can mathematically solve it and prove it. Right-hand side flow field is driven by the green boundary condition. So it's more tortuous heads. This right-hand side, these are string lines. showing the sort of the trajectory of the water molecules. This flow field also satisfies the 3 observed heads and 1 flow rate. What that means is that, no, why sometimes it works, sometimes it doesn't work. Okay. What that means is that both solutions yield 0 objective function because we have perfect match. Therefore, both fields are perfectly calibrated to the data. Results are therefore non-unique due to the different possible boundary conditions that in the real world you do not know. Okay, so if you do not know, you have to make guesses. I say non-uniqueness in theory. We have a detailed discussion which we published last year in this paper. Non-uniqueness in action. This is a problem of aquifer and the lake system being modeled in Wisconsin. Chen, 1994, assumed no flow boundary in this model domain based on some limited data. Then they calibrated this model successfully with 9 hydraulic conductivity zones and the 94 lake bed conductances, which is really the lake bed conductivity times lake bed zoned area because heterogeneous problem divided by lake bed thickness. So generally we can say it's successfully calibrated with about 100 different K values. A couple of years later, Hunt et al. 1998, they slightly modified the original no-flow boundary. See, this dashed line is the original no-flow boundary. They slightly modified based on additional data. They generate a new no-flow boundary. See that? It's very much similar, except here we have a no-flow boundary like that. Then, using the same objective functions and the same observation data, they successfully calibrated this model using 2 conductivity zones and 18 lake bed conductances. So a new model, a slight variation of boundary condition, a new model requires basically 20 conductivity zones so model results are non-unique. Different assumption of boundary condition yield different successfully calibrated model which minimize objective function between model simulated value and field observations. In a more recently, the biggest sort of hot topic is called hydraulic tomography. This is a transient method, so transient hydraulic tomography. Here we have a true model of log 10 transmissibility, so this is XY view. True model of log 10 storativity, XY view. Then these authors, 2010, have investigated transient hydraulic tomography where they calibrate the model using the true boundary condition. In the real world, we don't know the true boundary condition, but at least they are giving the true boundary condition to the calibrated model. Then they found out a set of calibrated models. This is log 10T, log 10S. Both models, using these parameters, the calibrated model generates the same hydraulic response of the true model. So they fit the true observation perfectly. But parameter calibrated by hydraulic tomography bear little resemblance to the true parameters. For example, here we have high transmissibility zones. In this realization, it's low transmissibility. Right? Storativity, same thing. We have something high values. Here is low values. And if the authors plotted the true parameter versus the inverted parameter, if they are well corresponding each other, they would lie along a 1-by-1 line. Instead, the two group of parameters has no correlation. So the results are entirely non-unique, even when they give a real boundary condition. So these kind of issues have been known in groundwater hydrology as well as in petroleum engineering since the 1970s. So when inverse methods were developed, people were aware of these issues. Our research is really motivated by trying to look at this problem in a different angle. And our goal is to, sometimes it works, sometimes it doesn't work, so okay, is to simultaneously infer parameters and boundary conditions while also accounting for subsurface uncertainty. So oftentimes we really do not know the true model. How can we account for the uncertainty? And these are the series of studies we've done. We've done a 2-dimensional inversion of confined aquifer first. Confined aquifer equations is simpler. Without salt sink, which means no leakage, no well effect. Then we figured a way to estimate a single conductivity and boundary condition. So that's a work we published last year. Recently, actually just last winter, I have done a study of inverting an unconfined aquifer with source sink effects and with or without wells, where I simultaneously estimated multiple conductivity, multiple recharge rate, and boundary condition. Even more recently, my students have been making rapid progress. We work on 3D inversion of confined aquifer without source sink. And we work out 2D inversion of confined and unconfined aquifers with source sinks. We estimate multiple parameters. Sometimes we can estimate conductivity as a tensor. So we don't have to be a scalar problem. We work on a little bit of stochastic inversion. So I will talk about that. And we even look at the fracture systems, because many inverse methods are very sensitive to the system variability. When K exhibits strong variation, some stochastic inverse method will fail. So we want to see if our method will be successful for very strongly heterogeneous system. Okay, so here let's introduce the theory just briefly for the simplest case we work on. Actually the year before, 2011, we started on this. It's a 2D confined aquifer without any source sink term. And it's homogeneous, and we assume the aquifer has several different K zones. So here the top part is one conductivity zone, the bottom part is another conductivity zone, kind of like two different formations. And under this simplification, we can write the groundwater flow equation. And this is our Darcy's law. This equation for given inverse grid, this is a two-dimensional inverse grid where this area that one grid cell, this is another grid cell. We can discretize the flow equation onto this inverse grid. The way we do it is that we actually write a set of approximation functions of hydraulic heads as well as Darcy flux components. These functions are written such that they satisfy the flow equation locally within a homogeneous zone where K is constant. Again, globally, we have different K zones, but locally, K is a constant either within a cell or within a zone, so we can write a simple function that satisfies the Laplace equation when K is constant. I should say mathematician probably can immediately work out how this plugged in, you get cancelled out, right? And this coefficient, so A0, 0, 1, 0, etc. This sort of describes the shape of the function. Because the function is unknown, these coefficients are the unknowns which we try to invert. Along with the conductivity. Conductivity is also unknown. So when we write Darcy's law, we invert conductivity along with these shape coefficients. Then with this function, we can write a set of residual equations. Here I just write a single equation which shows the integration of some residual function with a weight function over some sort of an element boundary or a measurement location. And we won't go into too much detail, but physically what that means is that, for example, if you have two elements here, at the element boundary, we want to enforce a continuity of the head function in the left-hand side cell with the head function in the right-hand side cell. We want to enforce the continuity of the flux component from the left cell to the right cell. We want them to match at the boundary. And if we have a K interface, K1, K2 aquifer, maybe there's some sort of confining bed, K is smaller. Then we enforce only two conditions: the continuity of heads and the continuity of the normal component of the flux. So it's no longer the two components, just normal components. This is to satisfy the well-known refraction principle in hydrology. The flow path will refract when we pass into a different material. So that's,
Excuse me.
okay.
Can I
Yeah,
ask
sure.
you? So HK in the XJ, YJ, these are the measurements that you have, right?
Oh, okay, no, this is actually approximation function written here.
So
They are approximation function because they satisfy the flow equation in a zone or in a cell. Oh, I almost skipped. This function we can also written for measurement data. For example, we have measured the water level here. Then we'll try to minimize the difference between the analytical function predicted measurement with true measurements times a weight which reflects the measurement error. So when the measurement contains a lot of errors, we do not trust the measurement as much, then we will have a weight that is smaller. So both continuity equation and measurement equation can be assembled when we call them residual equations.
So what do you call residual function? I'm sorry, I don't
Oh,
know what does it mean exactly, residual function? Is it
Oh,
the difference between your measurements and the...
Okay. If we're looking at the continuity of the function along the element boundary, the residual function will be defined as function 1 minus function 2. That's a two continuity equation. We want them to fit each other. So then, I guess we call them residual equation. Maybe mathematician will call them something else. But if we have a measurement point, the residual become a mismatch between model predicted value with the observed value. We call it residual. Actually, in hydrology, it's typical to call model predicted value with the difference between model predicted value with observation as a quote residual. So we wound up calling them residual equations. That's just how we sort of use these terms. Does it make sense? And okay. No, it doesn't work. Okay. So if we write all the residual equations for all the inverse grid cells, we can assemble a system of equations. In this case, they are linear equations. And if the system of equations is pretty small, we can solve with either direct solver, or if it's big, we may call a iterative solver. And we are solving these coefficients as well as unknown parameters. After we solve these coefficient unknown parameters, then every grid cell is populated with a set of functions, which means along the boundary, model boundary, where we have grid cells, we can recover the boundary condition from these functions. This is how our method does not require the knowledge of boundary condition. So we basically extend the mathematical solution all the way from the measurement location to the boundary. Oh, there's some regularization issues, we just skip that. Here are some results from our first paper. For example, this is a true model, 2D, XY, this is as a hypothetical model. We have a no-flow boundary condition. Here are some higher hydrolytic head, lower hydrolytic head. So given there are 4 different conductivity zones, K1, K2, K3, K4. Different zones have different K. Then if you solve this true model with a forward numerical simulator, you can predict the head contour in the aquifer. So high head flow goes like in and go out. Then from the true field, if we take 40 measurements of observed hydraulic head, and in this problem, 1 flow rate measurement. So if you anywhere in the model, we take a flow rate measurements. This is the head location. Then we use our inverse method. We recover recovered or calibrated heads, which are sort of similar to true heads. And more importantly, we can recover the boundary. So the solid line is a finite difference method true boundary condition. We assign the boundary. The dashed lines are the inverse solution obtained boundary condition. And we have 3 of them because when we add measurement errors to the measured data, if you measure water level, this measurement has noise. So when I increase the magnitude of noise, we will get worsened results in recovering the boundary. As expected, if your data contain too much noise, no method will really work. So that's sort of the idea. And we also work on the equivalent parameter case. This is a problem that because of subsurface access is limited, we cannot sample everywhere. We often do not know the detailed variation of the parameter field. So oftentimes we want to estimate some sort of a large scale equivalent value. So here is a true model. It's 2D model. K is a randomly we generate a K. Then when we do inversion, we assume we do not know the random variation. So we estimate a single parameter, we call it equivalent conductivity for the field. The idea the equivalent K can give us the mean flow rate of the true heterogeneous system. Okay, I'm not sure. Okay, so this is a true model, and because of the random field, the true equivalent K for this particular problem 2.7. And this we initially use a very low, weakly heterogeneous system of low variance. Then we take 25 observation of heads and 1 flow rate, no error imposed. Then we use the inverse grid, 30 by 30. Then we invert a single conductivity, 2.4. That is close to the true equivalent conductivity. Because our inverse method incorporates more physics, Therefore, our inverse solution reflects the physics of flow. So that's actually very, very exciting, these results. And when we...
How are you define your effective, your K-bar?
Yes.
The 2.7, how are you computing it?
Oh, this is a random system, so you couldn't catch arithmetic mean.
It's the arithmetic.
Arithmetic mean for random. But if it's correlated field, it's a different equivalent K. So it's not random, uncorrelated, white noise, basically. And we can also increase this, we also decrease number of measurements in this case. We take 15 samples, then we get something even better. Sometimes we have less measurement, we get better results. We don't exactly know why. And then we make the system more strongly heterogeneous. So standard deviation now is 1. Just means K varies in, you have higher peaks and lower valleys. K varies more drastically. Then our equivalent conductivity is similar to true but less accurate. The method definitely is affected by increasing variability of the data. For which case we later investigated, we need to add more data to get good results. So okay, that's another equivalent parameter. Let's skip this slide. 2D confined system, however, has limitations. We work on this problem. These are the limitations. We are basically coming up with some polynomial functions that will fit the mathematical equation. There's really no physics of flow yet. Source sink effect exists. These polynomial functions no longer provide a good approximation. I have tried, they do not work. And the previous study, we only estimate a single hydraulic conductivity because at the time we didn't know how to estimate multiple K. So we estimate K1, the problem with 4K zones, and we assume the ratio between K2, K1, K3, K1, K4, K1 are known. Then we from the ratio we get K2, K3, K4. Of course, that's very limited, right?
Excuse me, just for the second point.
Yes.
This, the sink effects, in the approximation that you showed before, you didn't show anything with the sinks, right?
Yes, that problem is without source sink effect.
Okay.
That's the simplest problem we solve before we can solve source sink. Okay. So since then, we were funded by 2 NSF EPSCoR projects, both of which are looking at Wyoming aquifers. And one project I'm heavily involved with looking at unconfined aquifer, shallow water table aquifer, which is, as we know, more nonlinear because of source sink effects. And it can also be very subject to strong boundary effects from background regional flow. Polynomial function, which I tested, did not work. And we bring in flow physics. The difference between earlier polynomial and the new method is that we superpose multiple analytical solutions. Each solution describes some source of either source sink effect or large-scale boundary effect. So in hydrology, when we assume homogeneous isotropic aquifer, we can write individual analytical solutions for different types of physical problems. So what I did here, I superimpose multiple analytical solutions as our fundamental solution of flow. And then because of non-linearity, all the residual equations, we similarly wrote them, but they become very nonlinear. So then I adopted the nonlinear optimization, which can allow us to simultaneously estimate the parameters and boundary condition. So we don't have to only estimate one conductivity. And we test for system for strongly heterogeneous system, because many of the aquifers as well as oil reservoirs in Wyoming are highly fractured. So our method will be useless if it does not deal with strong variability. Fracture conductivity can be orders of magnitude higher than the background non-fracture conductivity. So we test that. We also test conditions when the results are unique, but I will skip this part. We just don't have time for that. The new method, since we bring the analytical solutions for different components of the stimulus, sometimes we call it stimulation of the aquifer. I therefore call them physical-based inversion. So we bring the physics back into numerical inversion. For example, this is our unconfined aquifer flow equation written in 2D, right? Previously we generally solve XY, ignoring vertical flow. And we do a one-dimensional inversion. We start with simple. Let's invert the problem in 1D. And we have a pumping well somewhere. Our 1D, our origin R, is placed at the pumping well. And we have recharge. So we can write analytical solution for heads, for the recharge effect alone, for the pumping effect alone. But we can superimpose them because the equation can be linearized. We will skip the linearization part. I think which is too much information. But they can be superimposed to create a new approximation function. So this is not a polynomial function, but it satisfies the flow equation driven by different recharge-discharge event. And using Darcy's law, definitely we can use Darcy's law. We can write the analytical solution for fluxes as a function of R. And the conductivity N are spatially variable, spatially distributed. Then we can write a set of nonlinear equations which can be exact, underdetermined, or overdetermined. I will only show you the result of the overdetermined problem. Okay, so here is one result. Okay, the true model is 2 dimension. So we have an aquifer. This is unconfined. We have water table. We have 2 reservoirs which give aquifer the boundary condition. And we have 3 different conductivity zones, 3 different recharge zones. Usually higher conductivity generally causes more water to infiltrate through, so higher recharge rate. And we measure some water table elevation, so we have some observation wells. And we can measure either fluxes or flow rate. Then we simultaneously infer the 3 conductivity, 3 recharge rate, as well as boundary condition. The inversion in this problem is along 1D. This problem doesn't have a well yet, due to the Dupay assumption. But I think
in your approach, the location of the different zones is assigned by you. It is not determined as part of your solution.
right now, but later we work on stochastic problem where we don't know the zones. But in the interest of time, which I'm running out, I have to skip over all these results. I'm sorry. This is just, results are good. But let's actually say the 1D results are good, but we have to skip over most of the details. This is again 1D. We have a pumping well in the model center, 3K zones, 3N zones. And if you observe heads are error-free, true model are the black line. This is from well to the boundary. Inverted value are the red dots. These big circles are observation data. So when I perturb observation data with increasing error, you can see inverse result it still was stable. So it's very stable when we have increasing observation error. This is a problem and a similar problem, but we have a strong recharge rate. So we have now recharge basically bring up the water table. Again, we can calculate equivalent parameters. So we don't confine this. We can also calculate equivalent parameters. This case, we calculate K1, K2, K3, N1, N2, N3. This case, we calculate a single K equivalent and a single average N. So we don't know the patterns. This case, we calculate 3 different Ks and a single average N. Last case, we calculate a single equivalent K and 3 different N. So we can try and, okay, those are the true solutions and those are the 4 different problems. And they emulate, they recreate the true solution very well. We actually also tested the situation where the true recharge is 0. Rain never came. We then invert 3 parameters. And each of us give us a very small value. So the results are stable even when our true parameter is 0. Recently, we work on 2D inversion. This is a problem with, again, 4 different K1, K2, K3, K4 zones. And it's a confined aquifer with a single uniform N. So that's a finite difference grid. That's an inversion grid. These are the measured heads. Those are measured fluxes. And again, we have very good result. True model given true boundary condition. Hydraulic heads. Here are the inversion using the previous cells we just done. And they are very similar. If we look at heads along this profile AB, and you can see true solution is a solid line. Inverse solution are dots, which extend all the way to the boundary. We do not have measurements even very close to the boundary. We don't have to have that. The K, again, conductivity, true value compared to inverse results are very good. Recharge of the true value are well predicted by the inverse solution. So for this problem, we didn't do N1, N2, N3. We just use a single N. And let's move on. Okay, we also done inversion where conductivity is a tensor. So the confined aquifer, we have 4 different K tensors. And we sample some heads and flow field from the true solution. That's all we have, all the data we have. Then we invert for the true solution under increasing error, increasing measurement error. And this is a true solution of K, Kx, Kx, Ky, Kx, Ky. It's a diagonal tensor. And our inverse solution can be very good. Until, of course, when we increase the measurement error, the inverse solution becomes less good. But we can do tensor. Oh, we have also done simultaneous inversion of tensor as well, non-zero, n. This particular problem, n equals 0, but we will skip those results. Unconfined, okay, we also done a 2D with unconfined aquifer. And we just skip over, the results are again very good. So the equation is more nonlinear, the system of inversion are more nonlinear, but our inverse solution compare very well with the true model. This is our stochastic study. That's for my student Dongdong, where we don't know the zonation pattern. So if we have a true model, then we have 12 vertical wells. This is a confined aquifer, no source sink. From the wells, what do we get? We can get static data showing you the rock types, high K, low K, from which we can do a static data integration using geostatistics. Then we generate realizations of the possible rock types, which we first smooth. So we smooth them. I think Dongdong generate 100 realizations. So there's only 3 of them. We first smooth the realization, then we coarsen this, so our inverse solution system will not be too big. Then we have this realization of patterns. Then we bring in the dynamic data, which we also sampled from the 12 wells. Then we do dynamic data integration. As a result, our solution, those are the boundary conditions along this 2-dimensional model. This is a true boundary condition. Those are the boundary conditions created from 100 realizations. So we can estimate uncertainty in boundary condition estimation due to uncertainty about the subsurface true parameter patterns. So that's the part of stochastic. Again, conductivity estimated for one of the probably black facies of the rock. It's clustered around the true solution of 1. In this case, we use 12 wells, so there may be a slight bias, but it's a distribution. And another student of mine, Yifan, has worked on a very simple 2D fracture system because we want to see whether our inverse solution is still stable when we crank up the permeability, hydraulic conductivity variance. Here, a simple system. Let me just skip them. If I have done a system that's look more fractured, right? We have some red fracture zones, very simple fractures, which have much higher conductivity than matrix zone. Then we impose a true lateral flow. Then if I increases the conductivity contrast between fracture and matrix. So we're ranging from 10 times bigger to 1,000,000 times bigger. So now K fracture is 1,000,000 times more permeable than matrix. You can see that in the real world. Then our inversely calculated conductivity estimated for fractures, see the error? It's not sensitive to increasing magnitude of the contrast in the system. So that's very encouraging. We can use our inverse method to work on strongly heterogeneous systems where many inverse methods fail to address. Okay, I think I have 2 minutes. So we extend the method in 3D. It's very similar to 2D. For example, 3D, we have a 3D system of grid cells. We can start with something simple, confined aquifer, no source sink, no rain, no wells. We can write an approximation function for this set of equations. Here is written like that. Actually, recently we simplified this equation. This is an older slide, but we can solve it without using so many terms. So these are all unknown terms. Using Darcy's law, now we do confine, so 3 different flux components. We can write analytical expressions for these flux components. Then we write the residual equation similarly as we done for 2D. And of course, we have different conductivity zones. For example, in front of this red face, we have 1 K zone, another K zone. Then we will write continuity differently. Within a single K facies, we impose continuity of head, its first order derivative, and second order derivative. Actually, more recently, we found out we don't need to impose second order derivative. So, at the interface, however, because of the refraction principle in water flow, we only impose head and the normal flux and the first order derivative of the normal flux. And this is one simple example of a cube problem. Like some high head, low head, so we have a linear flow. This is true model K1. The top aquifer has smaller K, the bottom aquifer has larger K. So that's our true model from which we sample some measurements of heads as well as fluxes. And here, first of all, we did some sort of a convergence test because 3D is really even more complicated than 2D. Convergence test means when we refine the inverse grid. When we refine the grid, we find out this is the true model, the true K1 is 1. We showed K1. We find out when we refine the grid, if we use a complex approximation function, we can use a very small grid, we immediately get a true solution. But we can use a simplified function only with quadratic term. Then it takes a denser inverse grid to reach the true solution. So the grid density becomes important in combination with how we write approximation functions. And we also test the nonlinear flow. Previous linear flow just flow from high head to low head. Nonlinear flow, we have a corner head is high, a corner head is low, no flow on all sides. So we have flow coming in one direction and going out the other direction. With nonlinear flow, we also found that the quadratic expression tends to reach the true value faster than a cubic expression tend to reach a true solution faster than quadratic expression. So definitely the flow pattern itself affects the accuracy of inversion K1 true value is 1. So we have several factors. Flow pattern, very tortuous flow, approximation functions, cubic, quadratic, as well as grid refinement, coarse grid versus fine grid. They all affect solutions strongly. And I think we also did some sensitivity study to find out how much to measure. Just quickly, sometimes we have a linear flow model. This is a sensitivity study where we randomly take measurements. If we increase the number of observation data, naturally our results converge to a true model. But the idea is that when flow pattern is relatively linear, when we increase observation data, it changes very slowly. Meaning additional observation data improve inversion slowly. Nonlinear flow, different story. We need to take a lot of sufficient number of observation data to make the inversion to approach the true solution. So let's just quick, this again boundary condition. We look at some line sections through the model. Our inverse result, that's a true finite difference boundary. It's fit well. There's also some heterogeneous problem we tested. So they all fit very well. Boundary condition recovery is excellent. So far we have done a 3D. We have also done a sensitivity analysis. We will skip that. Basically to evaluate observation data worth. Where and how good the observation data must be to get good results. And today we also successfully tested the 3D codes for high variance situations. So 2D we tested up to 10 to the 6. 3D we tested up to 10 to the 5. And so etc. So they can be good in 3D, but 3D is really the continuum. We're still working on it. In conclusion, we have developed brand new inverse theory that allow us to bring in physics into aquifer inversion, both confined or unconfined aquifer. The physics often embodied in the analytical solution. We can simultaneously estimate multiple parameters and boundary conditions. The parameter may include conductivity, sourcing terms. And given sufficient data, solutions are unique. We can actually find unique solutions, including the boundary. So far, this kind of thing has not been done. Solution are stable when we increase measurement errors. So I use up measurement error up to positive negative 10%. Right? That's huge error, but solution was stable. Computation efficient. Traditional, the current most inverse method need to solve the forward model multiple times, sometimes thousands of times to use global optimization. We only solve it a few times. If we use a stochastic study, we maybe solve 100 realization 100 times. If we do a deterministic study, we solve it one time only. We can account for data uncertainty due to limited measurements. So that's a stochastic study. If the underlying parameter is unknown, we can get equivalent parameters. Sometimes all we need in large-scale aquifer studies are just the equivalent parameters, not the point-by-point parameters. So that is the very exciting part. We can get physically meaningful parameters from inversion. And our inversion is not sensitive to high conductivity contrast. 2D up to 10 to the 6th, 3D up to 10 to the 5th, successfully tested. Okay, future work, of course, we have a lot more. We just started. We are ongoing, we're doing sensitivity analysis to evaluate data worth. Where, how good the data must be. And we want to work on multi-layered system. In the real world, we actually have multiple aquifers, multiple confining beds, and on top of that, we have unconfined aquifer. So when we have multi-layered system, the physics gets more complex, and we have some idea about how to work on that. We, of course, are interested in highly parameterized inversion, where you can invert parameters at every grid cell location. And here we have some ideas. For example, we can use simple stochastic functions to describe parameter spatial correlation, which will yield additional constraint equations. We can also condition our methods to geophysical data that are correlated to hydraulic parameters. So this is, I should say, very exciting. That's why I'm involved with the Tract 1 project. And we're going to go to the field and collect the geophysical data, which we're going to incorporate into our inversion, and we can then look into the aquifer at greater details, which means more parameters. And we can look at a whole bunch of other situations where analytical solutions have been developed for simplified subdomains, then extended in our work to do the aquifer inverse problem. Okay, that should be the end of my talk. I'm 5 minutes over.
You got a lot of questions before. I have a question.
Sure.
About your one of the conclusions.
Conclusions?
Since
Okay.
you are talking about computationally efficient.
Yes.
Can you quantify the error, for example, with respect to the number of data that you collect, or can you quantify it? How good is your error?
Inverse results. You mean inverse calculated parameter and boundary
But at a
condition?
certain point, you say computationally efficient. Are you computing some error estimates, or
what
because you
I
are quantifying like you know the approximated solution with
Okay.
respect to the true solution? Yeah, right. At a certain point, you have graphs.
what I mean here is how many times do we have to solve AX equals B? How many times do we have to do an optimization solution? When we have a deterministic pattern, we solve a single set of AX equals B, or a single set of FX equals 0. So we solve it once, but the common method is to design objective function, which you need to solve the forward model many times with different parameter combinations. Then each time you solve it, you evaluate objective function. Then you keep solving the forward problem until objective function become very small. Then you say, maybe we have found the correct parameters or boundary condition for inversion. Since we do not use objective function, we do not need to solve the forward problem multiple times. We basically solve an inversion optimization, which is one set of equation if we're solving a deterministic problem, which is that if we solve a stochastic problem, we solve it maybe 100 times. One for each realization of the subsurface static model. So maybe we haven't got to what you are suggesting.
No, I mean, no, it's okay.
Okay. Question?
So on the second to last conclusion there about the underlying parameter heterogeneity is unknown, equivalent parameters, is that still true if the heterogeneity is in both space and time? So if
That's
the
a-
variables sync in space and time?
We have not done transient problems yet. I should say in the early equation, I should cut off the right-hand side. Right now, we're looking at a steady-state flow system where things are not changing very much with time. So we have steady-state flow field, and so we cannot yet deal with the effect where you have a sudden rain event, then maybe water table jumps up. No, we are actually looking at in between rainfalls when the water table is mostly stable, where we have flow field that doesn't change with time, where we do our inversion. So transient, not yet. But we hope we will be able to figure out transient inversion as well once we get to it.